Faculty Development Program of Innovations, Machine Learning, Artificial Intelligence, Data Science, and Modeling. Today's session is going to start with one of the eminent researcher, Dr. Sujit Das, sir. Dr. Sujit Das is presently working as Assistant Professor in the Department of Computer Science and Engineering, NIT Warangal. Coming to academic, he has 21 years of teaching and 12 years of research experience. Dr. Das specialized on soft computing, AI, ML, and multi-cloud decision making. Dr. Das published more than 70 papers in high indexed journals and 1850 plus citations also. Dr. Das got 3 best paper awards during conferences, one from the CSO 2015, second one from FICTA 2015, and FORBS 2018. Dr. Das has been designated as IEEE senior member by IEEE Society. And coming to Dr. Das organized several FDBs, seminars, etc. And this is a brief biosketch of Dr. Sujit Das. Now I request Sujit Das sir, please give your valuable talk for participants. Welcome you, sir.
So thanks for this nice and brief introduction. So really, I feel fortunate so that I got the opportunity to share my thoughts on this nice platform. Innovations in machine learning, artificial intelligence, data science, and modeling. So whatever the recent buzzwords today we are using, I think this FDP is almost covering everything. So I am really thankful to the coordinators of this FDP for their kind invitations. And yesterday I reached here at around night, at around 12:30, but I found this is a fully green campus, actually enjoying my stay in guest house. Anyway, so once again, I want to thank the administrations and Department of Mathematics particularly for communicating with me and to invite me to share my thoughts here. So with this, we will start my session. So this session is all about this multi-objective optimization and its applications. So as you know that today, whatever we are working with, it may be artificial intelligence, it may be machine learning, or it may be data science. So for each and every place, actually, you will find out some applications of optimization techniques. As you know, if we say that particularly for machine learning, particularly if I say that for artificial neural network, if we go for back propagation, feed forward neural network, you will find out gradient descent algorithm, we are using it. And also, if you check that adaptive neurophage inference system, which we say NFIS, there also you will find out that to optimize the premise and consequent parameters, you are using optimization techniques. Now, sometimes the optimization techniques, maybe it is single objective optimization, and sometimes we may say multi-objective. Actually, there is some difference between single objective and these multi-objective optimizations. So today we'll start with this single objective optimization, and then slowly we'll move forward to this multi-objective optimization. You know, in our real life, in our real world actually, so whatever problems you are facing, if you want to solve the problem, you should take help of this multi-objective optimization. There perhaps single objective optimization will not be helpful for you. But yes, we need some basic idea of single objective optimization so that we can set the platform to discuss about this multi-objective optimization. Okay, sorry. Okay, fine, thanks. So initially, we'll start with this optimization, then slowly we'll move forward from single objective to this multi-objective optimization. Mainly we'll discuss today genetic algorithm. Multi-objective optimization that may be possible for each and every optimization algorithms. But today I thought that we'll start from genetic algorithm only. Then we'll discuss some important case study that is NSGA2, which is having some significant effects in the context of this multi-objective optimization. And then we'll try to find out some future research areas in the context of this multi-objective optimization. Now, initially, we need to know that what is optimization. I think I no need to tell, needless to say that all of us, we know that what is optimization. So simply, I can tell optimization means to make something better. Now, once I'm telling to make something better, so here, see, check it carefully. I'm never telling to make something best. Instead of best, here I am telling the keyword better actually. So then question may be there, why we are using these optimization techniques to make something or some of our problems, we should get some better solutions. Why we will not search for the best solution? As you know, one important statement is that none of the optimization techniques will give you that particular of based solutions. Rather, all of the optimization techniques will help you to get the better solutions. Then why it is required? Why we are going for this better solution? I can tell you some example. Suppose you are using some GPS navigation system. Actually, yesterday I was using the GPS navigation system. Once I arrived here in guest house, then to check what are the various departments. Then I found that it was showing some long paths moving here, there, here, there. Okay, this is the seminar hall, and this is the other departments, this is the administrative building. And today, once I was coming, I found no, it is not that much complex. It is straight only. So now see the situations. So whatever you are getting using this GPS navigation system, obviously it is showing us some optimized path. But is it the path which is the best path, or it is not the best path, it is the better path? If you see clearly, then whatever path it is showing using GPS navigation system, so it is not the best one, it is the better one. Because if it needs to find out the best one, it may take maximum or some major amount of time. While if you go for this better one, it may take fraction of a second, you will get the solutions. That means obviously you will go for that. So optimization technique means using that we will get fast enough, we will get good enough solutions in a fast enough manner. There is another statement behind the optimization techniques. If you apply, we will get some good enough solutions in a fast enough manner. That means in a reasonable amount of time, you will get the better solutions. And also for some of the problems, today we are working with this all NP hard problems where that problem complexity increases, okay, once input increases. That means that is very much difficult to solve those problems using simply our classical or traditional models. Then we need to take help of this optimization techniques where it will give you the optimized solution. That means better solution irrespective of the best solution. And what we feel that here I have mentioned something search space actually. So what we feel that search space, that means initially what we feel that in the search space, we have some set of solutions. So what is our target? Solution means here I mean to say in the search space, we have some set of feasible solutions. Feasible means what? Feasible solution means obviously that's a solution that is satisfying all the hard constraints and as well as it is satisfying some of the soft constraints. So what should be our target? So in the search space, we are having some set of solutions. So our target will be to find out which is the optimal one from this set of solutions. Now, more mainly heuristics and meta-heuristics techniques we are using to solve these optimization techniques. Okay, so here I'll tell you that some differences are there between heuristics and meta-heuristics. Whatever I tell heuristics, that means this is some innovative ideas, or better I should say, that is some different approaches which are totally different from this classical or of our traditional approaches. And once I say meta heuristic, see that here one keyword is added with the heuristics, that is meta. So what is meta heuristics? If you search in Google what is meta heuristics, so it will give you heuristics of heuristics, that is called the meta heuristics. But that is exactly not the definition for this meta heuristics actually. It is not about heuristics or of heuristics. It is actually something else. I should say meta heuristic means that is beyond heuristics. Actually, heuristic approaches, that is some different kind of innovative approaches. So we will apply obviously to solve some optimization problems or of our real life problems. But as you know, that heuristic approaches are very much problem dependent. So each and every problem has its own heuristics to solve it. You know, if we take some searching or sorting problem from the data structures, how to solve all these problems? What about the searching or this sorting algorithm, you know, maybe that belongs to the heuristics. But what is meta heuristics? As I said, meta heuristic means sometimes meta heuristics may be nature inspired, sometimes meta heuristics may be physics, chemistry inspired, sometimes it may be some swarm inspired. That means whatever happening in and around us, simply out in around us inside the nature. So we are taking the ideas from the nature and we are trying to implement the same thing in the context of our this algorithm. No, meta-heuristics algorithm, it has basically wide applicability compared to the heuristics algorithm. And here I should say one more thing, that meta-heuristics, these algorithms are simply problem independent. That means if you want to solve some problem, simply you need to map your problem. If you need to map your meta-heuristics to that particular problem, so that you can solve it in quite reasonably, quite efficiently and as well as in faster manner. So I hope now, so the difference between heuristics and meta-heuristics is a little bit clear. Now, you know, so once we'll start with this meta-heuristics algorithm, then it may be of two types actually. As I told, that behind once you are starting with these heuristics or meta-heuristics algorithms, you are starting with a search space. And as I told, that in the search space, we have some number of solutions. So what is your target? What about the feasible solutions we have in the search space? We need to find out which is the better one, which is optimized one. Here, optimized means I need to say which is better one. Again, you know that optimize, it may be of two sense. You know, once you are using criteria as cost, obviously you'll go for minimizations. Once you are using benefit as your criteria, obviously you'll go for maximization. So optimize, it may be maximize or it may be minimize. If our criteria is cost, obviously you'll go for cost minimization. If our criteria that is benefit, then obviously you'll go for this benefit maximization. Now, again, let us come to this point. So all of this meta-heuristics algorithm, so it may start with a single solution. Again, it may start with a multiple number of solutions. As I said, the search space is there. In the search space, number of solutions are there. So some of the meta-heuristics algorithm starting from a single solution and slowly searching the entire search space. And some other meta-heuristics that is starting with a pool of solutions. Pool of solution means it is starting with a multiple number of solutions and then simultaneously trying to update this multiple number of solutions actually. So what should be our objective? Now see, if we say right now, once we have the search space with us, we are in the initial first generation. So once we'll move from first generation to the second generation, so what should be our target? First generation, we have some initial set of solutions. Okay, so what should be our target once we move from first generation to the second generation? At least to improve the solution quality. Now, how to describe the solution quality? You know, fitness function or optimization function normally used to identify or to determine the solution quality. Once we are moving from one generation to the next generation, obviously, or one iteration to the second iteration, obviously, average solution quality should be improved. Because ultimately, our target is that we want to get the better solutions or optimized solutions from the set of feasible solutions. Next slide, next. I think sometimes it is, it is not working. Huh? Anyway, it's okay, no problem. So we'll proceed actually. Sometimes it is not working what I'm finding. Okay, otherwise no problem. Please give the keyboard here so that's that I can manage it. Okay, okay. Now it's okay. So these are the categories of this. Okay. Wait. So here, so see meta heuristics, as I told, sometimes it may be single solution based meta heuristics, and sometimes it may be population based meta heuristics, single solution. That means in the search space, we have a single solution. In the search space, as you know, we have a number of solutions, but we are starting with a single solution. And then slowly we are trying to update that particular solution. And what about population based? As I told, so here in the so in the population based, what I told that in the search space, we have a multiple number of solutions. We have a pool of solutions. And what we are doing in each and every iterations, we are trying to update the average solution quality. Now, population based meta heuristics may be again two category, evolutionary algorithm and the swarm intelligence algorithm. So today we'll come to this category, evolutionary algorithm only. Next slide, okay, next. Okay, it may be some technical issues. Okay, no problem. Slowly we'll proceed. Sometimes these things may be there. You cannot avoid actually once you are presenting in hybrid mode. This is very normal situations. Okay, so let us. Okay. So as I told that meta-heuristics algorithm, as I told that it may be nature inspired. Okay, it may be physics, it may be inspired from physics, it may be inspired from chemistry. As you know, once meta-heuristics algorithm are getting inspired from the physics, what is the law of physics? As you know, if we apply some heat to some materials, okay, and then suppose applying some maximum heat to some materials and then slowly cooling it down, then what will happen? Ultimately, the materials particles will be restructured and the material will be much more stronger actually. That thing will be much more stronger. So that is called simulated annealing algorithm. That is one of the meta heuristics algorithm. What simulated annealing actually, it starts with a single solution. And if I say that how the flock of birds are moving in the sky, okay, suppose in a particular position, some food source is there, then you will find out the birds, the flock of birds, once they are moving in the sky, automatically they are reaching to the food source. How they are reaching to the food source? If you look carefully that how birds means what? Birds means here each and every solution. So how the birds are changing their position, communicating with each other, and ultimately moving to the food source. So based on that, researchers has developed this particle swarm optimization. And again, if you see that how ants are searching for their food, if I place one some sort of sugar here, if I come after 3-4 hours, if this area is not that much maintained by pest control, you will find out after sometimes all the ants will be in a big queue. How they are getting that here some sugars are there and they are coming to it. So based on that, researchers has developed actually ant colony optimization. That is another this meta heuristics techniques. Today, our topic is evolutionary computation. As I told that we will be mainly discussing with genetic algorithm. So once I need to tell this evolutionary computation, actually this is a subfield of this artificial intelligence and soft computing. So today all the buzzwords, whatever it is written, artificial intelligence, machine learning, data science, maybe deep learning. So if I take a big circle, that is our artificial intelligence. Then smaller one inside that, that is machine learning. Machine learning is a subset of artificial intelligence. Again, one more smaller circle inside machine learning, that is our deep learning. Deep learning is a subset of machine learning. And what about data science? Data science, so in another side, I will put one more circle. That means data science, it takes everything from artificial intelligence, machine learning, deep learning, as well as it has its own characteristics. So that means data science is something different. It is taking all features from all the JIML deep learning, as well as it is having its own feature, mainly that is coming from the data mining. Anyway, so that we are telling that evolutionary computation, whatever you are discussing, that is a subset of this artificial intelligence and these soft computing techniques. Now, what I told, this if you look carefully to this statement, see, each new generation is produced by stochastically removing less desired solutions and introducing some random changes. Actually, here what I told that today, whatever you are going to discuss genetic algorithm, so that is starting from a pool of solutions. It is not starting from a single solution. We have a search space, multiple number of solutions. It is starting with a pool of solutions. And then what will be our target? Our target is once we'll move to the next generation, that means we need to update
So,
the average solution
sir,
quality.
sir,
We
am I
need to
audible, sir?
we need to
Sir, am I
update
audible,
that.
sir?
Yes, you are audible, please. So
Good
we need
morning,
to
sir.
update.
Good morning, sir.
Yeah, good morning. Do you have any questions?
Sir, yes, sir, yes, sir. Sir,
Yeah, please. Yes.
what should we mean by stochastic, like you have said,
Probabilistic.
few,
Stochastic, yeah, stochastics means probabilistic actually. So here once I will proceed, I will show that how these stochastic features we are implementing in this optimization techniques. Stochastic is
yes, sir.
nothing but probabilistics. That means in each and every optimization techniques, we need to apply some randomness. Okay,
Yes, sir.
whatever optimization techniques we are discussing, each and every techniques has some their inherent tendency that they may stuck in local optima. Do you know the concept of local optima and global optima? Actually, for some solutions, there may be multiple number of local optimal solutions and as well as one global optimal. That means, actually, I don't have, but if could I have board here, I can explain it much more better manner. Anyway, so that
Yes,
means uh, some solutions may be locally based, some solutions should be globally based. Now, what we will look for? We will look for the global based. That means if we see that we are taking some example of hill, then it may have some multiple peaks. It may have some multiple peaks. Okay. So one may be the top peak and all others may be besides this smaller peak one. So what is our
yes,
target? That ultimately we need to cross all these smaller peaks and we need to come to that top that is high, bigger peak in a particular hill. That I mean to say, which is bigger one, that is our global optimal solution, which are the smaller ones, that is our local optimum solutions. Once you are proceeding with some optimization techniques, there is a tendency that you may stuck in local optima. So by including the feature of stochastics or randomness features, so we are trying to come out from this local optima. Now, is it clear for you?
yes, sir. Thank you,
Okay,
sir.
thank you.
Thank you.
Okay, thank you, thank you. That was a very good question actually, that what is stochastic or how we are implementing these stochastic features in these optimization algorithms. Okay, so what should be our target now? So we are starting with a population. We are moving to the next population in the next generation. Now, if you see that once I am telling regarding some population, uh, actually some board could have been arranged. It will be better. Some board can I arrange here? Board so that I can write something actually. Okay, otherwise, okay, we'll proceed. No issue. No issue. Sit, please sit. Okay. So what I mean to say, see population. So what is population? So population means some set of solutions. Population means some set of solutions. So initially we have some pool of solutions. Let us say we are starting with 10 number of solutions. That means once we will move to the next generation, we will have exactly 10 number of solutions only. We will move to the third generation. We will have 10 number of solutions only. That means each and every generation, what are the solutions in our population, that will be fixed only. So what is our target here? Our target here to increase the average fitness of the population. What is there inside the population? A set of solutions are there inside the population. So once we will move from generation to generation, our target will be to update the average fitness value which are there in this population. Average fitness value of the solutions which are there in this population. Okay, next. Okay. Now, for any evolutionary computation, mainly two things is there. One is genetic inheritance. Second one is the natural selection. Now, if you look closely, that naturally, which things are getting selected? That has a higher chances of survival. During COVID-19, we lost some of our colleagues itself in NIT Warangal, or maybe from some other places, we lost our students also. That means what we can say, and somehow due to the luck factor or due to our more survival capability, we got survived. So what we should say actually? So naturally, who are surviving, who are vanishing? Those who are adaptive to the changes in nature, they have a higher chance to survive. Those who are not that kind of adaptive, that kind of things that they cannot adapt in the changes of nature, simply they will vanish. So natural selection that we are using in these evolutionary computations as well as genetic inheritance. This is another thing. What is genetic inheritance? Normally we feel that if parents are better, their children may be better. Let us say if parent solutions are better, so whatever the child solutions we will get, obviously that are supposed to be better. So this is coming from this genetic inheritance. Exceptions are there, but this is coming from genetic inheritance. That means if we apply two solutions, okay, and if we apply some crossover between two good solutions, so what you can expect? We are having two good solutions, applying crossover on those two good solutions. Let us say here from those two good solutions, once we are applying crossover, we are getting to child solutions. So what would be our expectations? If parent solutions are good, once we are applying some crossover, obviously as a result, once we are getting the child solution, expected to be much more better. So that genetic idea actually we are using in this evolutionary computation. So two things are there, as I was telling, genetic inheritance as well as this natural selection. So this is the principle of natural selection. As I mentioned, select the best, discard the rest. That means obviously those who are adaptable to the changes in nature, will keep them. We'll keep those solutions and we will reject those solutions which are not adaptable to the changes in nature. What does it mean? It means that we will keep the best solutions, better solutions, and we will remove the worst solutions once we are moving to the next generation. But is it like that? Is it what I am right now I'm telling? Is it the natural selection? Only we will keep the better solutions and we will remove the poor solutions once we are moving from one generation to the second generation. Will you go for that? Or maybe some solutions you will keep, which are some poor solution also. So now see, so if I give you some example, then the things will be very clear. Next slide. If I give you some example, then the things will be very clear. Now see, so check this example. So if I say that all the giraffes are having long necks, I think you will say, yes, it is true only. All giraffes have some long necks, but I should say it is false. All giraffes don't have the long necks. Few giraffes are there who have short necks also. Now see the situation. So initially giraffes were there who are having short necks as well as longer necks. Then what happened actually? So then who are getting survived? So as time passes, giraffes with longer neck, they are finding survival capabilities more. Why like that? Because initially what happened? So once the leaves, in the lower branches of the trees, more or less it was over, then giraffes with the higher neck, they got the opportunity, yes, they can eat the leaves from the lower branches as well as from the higher branches. But giraffes short necks, what they found? They found it really challenging to survive once that leaves from the lower branches were eaten off. It was over actually. That means, see, so initially, both are having equal probability, but slowly, probability of getting survival of the giraffes with the longer necks are getting more. Probability of survival for giraffes with shorter neck are becoming less. So that means, should I say giraffes with short neck totally vanished? Should I say that? No, no. Giraffes with short necks, by chance factor, few giraffes are there today also. By the chance, by the luck factor. This is the stochastic actually. Okay, this is the randomness. See, once we are moving from one solution to the one generation to the second generation, what we are telling? Our target is to maximize the fitness value. That means we want to keep better solutions from one generation to next generations. Let us say giraffes be our solution. So what is happening? In the next generation, obviously good solutions will be there. More number of giraffes with long neck will be there. But as well as some giraffes with short neck also will be there. Can we avoid that? We cannot avoid that. Some of the giraffes by luck factor, by chance, also they are moving to the next generation. It is not possible. This is stochastic in nature, randomly. That means what I should say, once we are moving from one generation to the next generation, In the next generation, obviously, more number of better solution will be there, but as well as poor solution also will be there, but they are less in quantity. You're getting the facts. It's not like that. Once we are moving from one generation to the next generation, only better solution will be there. No poor quality solution. No. More number of better quality solution and less number of poor quality solution will be there. Like this example, actually, giraffes. Actually, again, you can ask me, sir, why the situation is like that? Why you are considering more number of better solutions, less number of poor quality solutions? Why you are thinking like that actually? Why you are not considering only the better solutions in the next generation? So the idea is like that. If you consider only better solutions in the next generation, then you may stuck in local optima. Because better solution means that maybe the shorter peaks in the hill, smaller peaks. So sometimes from the small peaks, you need to come down to reach to the big peak actually. That means sometimes you need to select poor quality solution also. We are moving from this to this. So this is my peak. These two side, four solutions are there. Sometimes you need to come down from this peak and so that we can go to the higher peak. Now see the actually thinking thoughts behind it. So that is the requirement that sometimes stochastically, randomly, we need to consider some poor quality solution also so that we can come out from this local optima. So that is the natural selection. Now you are getting how natural selections are being applied in this optimization techniques or evolutionary computation so that we are coming out from the local optima, we are reaching to that global optima. So as I told here that all these optimization techniques, we will find out some good enough solutions in a fast enough manner. Okay. Now let us quickly come to this various terminology, whatever we will apply today. Population. Already you know what is a population? Pool of solutions. Chromosome. Each and every candidate solutions, I mean to say one chromosome. Each and every candidate solution. One solution, one chromosome. Now what is the gene? So gene means it is nothing but the parameters of the chromosome. You know, if you consider I think this TSP, traveling salesman problem, then what will be your solution? You know, traveling salesman problem, I think all of you know what is traveling salesman problem. Traveler or salesperson is there, starting from the initial city, will visit all other cities at most one time, come back to the initial city. So initial city will be repeated, all other city will not repeat it. And then objective is to minimize cost or to maximize benefit. That is traveling salesman problem. So in traveling salesman problem, what will be chromosome? Suppose 1 to 10 cities are there, maybe started from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, coming back to 1. This is one solution. What is the second solution? 1, 5, 7, 9, 8, 3, 2, coming to 1. We are changing the permutations of the cities. So that is another solution. So what are the cities? So cities are nothing but genes. Now see, parameters. So gene means, so this is the parameters of that particular solution. LE, this is the value. And again, two things is there, genotype and phenotype. So mainly you need to understand what is chromosome, what is population, and what is gene. Chromosome, one candidate solution, and in a population, since it's all about genetics, that means what will happen? Chromosomes. If we consider a chromosome, one solution, inside chromosome, number of genes are there. As I was telling, so genes will consider the parameters of the solution. If traveling salesman problem is our problem, then gene value will be the number of cities. Various cities we will consider as gene here. Now, fitness functions, as you know, what is fitness functions already I told. Fitness functions we will use in this optimization technique to find out the goodness of a solutions. Most importantly, I should repeat it. Genetic algorithm, what is our topic of discussion? So that is inspired by this Darwin's theory of natural evolution. Darwin's theory, this is not any other theory. This is Darwin's theory of natural evolution. What is there? Organism, or this is organisms that are poorly suited for an environment, they will vanish, while those well suited, they will prosper. But is it like that? You are applying directly this natural selection. Here written, organisms that are poorly suited from an environment, they will die off. Those well suited, they will prosper. But what we are telling? Those who are well suited, okay, they will directly move to the next generation. But those solutions are poor quality. Again, we will select some of them. They will survive by chance. They will survive by their luck factor. Okay. So genetic algorithm will start with the initial solution. Try to understand it. Here it is a population based. So that means we are starting with a initial set of solutions, initial set of chromosome. That means suppose we are starting with a 10 chromosome. Okay, we are starting with a 10 number of chromosomes. Just see, listen what I am telling. We are starting with a 10 chromosomes, and suppose what I am telling, chromosome 1, or let us not to take 10 chromosomes. Let us make it simple. You are starting with 5 chromosomes. Okay, chromosome 1, I am telling fitness value 10. Remember, chromosome 2, fitness value 20. Chromosome 3, 30. Chromosome 4, 40. Chromosome 5, 50. Fitness values. So what I mean to say fitness values. Suppose assume this is a maximization problem. Fitness value more, that is a good quality solution. Okay. So what is the average fitness value right now? 10 plus 20 plus 30 plus 40 plus 50. I think all mathematicians are here. They can compute much more faster than me. So what is the average fitness value here? 10, 20, 10 plus 20 plus 30 plus 40 plus 50. What? 30. Okay, so average fitness value is 30. So this is our first generation. Okay. From the first generation, now we are moving to the second generation. So what should be our target? At least to increase the average fitness value. And right now it is 30. In the next population, what is our target? It's at least it should cross 30. Now see how it will be more in the next generation. So what to do? See here, we have 5 solutions, 10, 20, 30, 40, 50. 5 solutions. Fitness values are those. Average fitness value right now 30. Our target is once we'll move to the next generation, average fitness value should improve. Now apply natural selection there. What natural selection is telling? In the next generation, more number of good quality solutions will be moving, and less number of poor quality solution will be there. But number of solution in the next generation also will be fixed. What is now right now number of solutions? 5. 1, 2, 3, 4, 5. In the next generation also number of solution will be 5. Apply natural selection now. So if we apply natural selection, that means my solution, fifth number of solution, fitness value was 50. So that means it will be copied in more number. 50 may be repeating 150. That means now I have solutions or 2 solutions having the fitness value 50. Okay, and I am discarding the solution which has fitness value 10. Now check. So that means 250, 20, 30, 40. What is the average fitness value? 250, 20, 30, 40. That's why I thought that that board may be much more helpful for me actually, because all about mathematics this is. Are you getting? So one poor quality solution we have dropped. Solution number 1, fitness value was 10, we have dropped. But you can tell, sir, solution 20, fitness value is less only. Why you are not dropping? I should tell, I have not dropped by in making some biasness to solution number 1. Randomly, I am picking some poor quality solutions and dropping. Okay. So what is happening? Are you getting now? So we have 2 solutions, fitness value is 50. Remaining 3 solutions, fitness value is 20, 30, 40. Average fitness value is increasing or not? Yes, average fitness value is increasing. See, this is natural selection. More number of good solutions, we are shifting to the next generation in more number. 52 numbers. But poor quality solutions, we are dropping. But again, all these things are getting done randomly. That's why it is stochastics. Randomness is there. I have no biasness. I should not tell, okay, you should repeat 50 only. System is taking randomly. That means system may repeat 30 also, 40 also, I don't know. System may repeat 20 also, 10 also, 30 also. It may remove. That I don't know. Everything is getting done here randomly. We have no biasness to any solutions. Okay. So that's I told. We are forming a new population is formed by old population and offspring based on their fitness value. Now see, here I have given a term offspring. Our natural selection is over. Once our natural selection is over, we will go for some crossover, I think I should say that some operators actually will find out. It may be crossover operators or it may be some mutation operators. Some genetic operators we will use once our this natural selection is done. Natural selection, we are copying more number of better quality solutions in the next generation. Next, we will apply crossover. This is one kind of recombination operators. Crossover we will apply. Crossover, what I told. Randomly you select two solutions. Apply crossover. What I told. If you randomly select two solutions, apply crossover. As a result, you will get two offspring solutions. Now see, after natural selections, what population we got, there are actually more number of better solutions are there in comparison to our previous population. Now we are right now in a population after implementing the natural selection. So try to visualize the idea. Try to visualize it. After implementing natural selection, we have moved to the next generation. So in next generation, what are the solutions we have? More number of good quality solutions we have in the next generations. Now, if I randomly select two solutions from the next generation, then what will happen? What is the probability? Probability of selecting good solutions are more because we have more number of good quality solution. So probability of selecting good solution will be more, and then apply crossover. Now see the situation, applying crossover. Once we are applying crossover, what will happen? Crossover itself, it is telling we are taking it from this genetic property. Here we are telling if parent solutions are better, if you are applying crossover, whatever the offspring solutions you will get that are supposed to be better. So average fitness value will be increasing or not. Automatically, if you can visualize it, average fitness value will be simply increasing only. See the situations, how all these things is coming into picture. Okay, natural selections and this genetic inheritance. Simply you are applying these two concepts in your algorithm and things are getting changed here. What initially expected, average fitness value should be improving. So by applying crossover, by applying natural selection, yes, you are finding average fitness value is increasing. Let us say, suppose randomly selected solution number 50, solution number 40, apply crossover. Okay, applying crossover, we are selecting two solutions. Solution number 50, where the solution having fitness value 50, another solution having fitness value 40. Apply crossover. You will get two offspring solution. Once you will get two offspring solution, what it may be, what are our expectations? Here fitness value may be 60, maybe 45 or 50. At least it will be better. This is our expectation actually. So average fitness value is improving or not? Yes, average fitness value is improving only. But again, it may be, should not be always the case. Sometimes it may decrease also because everything we are doing randomly. But what probability is telling? Probability is telling, okay, maximum probability is that average fitness value will be increasing only. Since probability of selecting good solutions are more in case of crossover. So probability is telling obviously there is a more chance that it will be increasing. Sometimes it may decrease also. Now this is our actually flow chart for this genetic algorithm. So see, so initially we will create a population of chromosomes. As I told, chromosome means nothing but solution. Determine fitness value of each and every individual. Fitness value means what? Fitness value, it will give the quality of a solution, goodness of a solution. Now you may feel, sir, how you will find out the fitness value for some solution? Now, if I take the example, traveling salesman problem, how you will find out the fitness value for traveling salesman problem? Can anyone tell me how to find out the fitness value of a solution for traveling salesman problem? How to find out fitness value of a solution for TSP, traveling salesman problem? How to find out the fitness value? Can anyone tell? If you take cumulative, if you take summation of all the path cost, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 9 to 10. If you take summation of all path cost, that will give you a cumulative cost, total cost. That is nothing but the fitness value. That is the fitness value only. Now what I told, once you are moving through all the cities, that means cost should be minimum. You should visit in such a manner, cost should be minimum only. That means how you should visit. You should need to take care of the cost only now. So fitness value for TSP will be summation of all path cost, which cities you are visiting. So similarly for each and every problem, you will get some fitness value. Next, select next generation. Select next generation. So initially you are in first generation. We are moving to the second generation. Once you are moving, you are applying natural selection. We were initially in first generation, we moved to the second generation, applied a natural selection. What happened? Average solution quality becoming more. Natural selection we applied. Okay. Next, we will apply this reproduction operator, crossover and mutation. Already you know what is crossover. Now, what is mutation actually? Mutation means, I mean to say, random changes in genes. Sometimes a solution quality may be very much poor. But if you do some changes in the gene means what? Parameter only. So if you do some changes in the parameter values, random changes, I mean to say, stochastically do it. If you do some random changes in the gene values, what it may happen? Solution quality may be much more improved. Think about this traveling salesman problem. Okay. So simply you drop one node. So simply you drop one node, you put another node. What may happen? Cost may be changing now. Node means what in case of traveling salesman problem? One node means one city. Okay, randomly drop one node, insert another node there. What may happen? So cost may be more, sometimes cost may be less. It may be of two cases. Okay, but why I am telling that, what I am telling that is the solution will be improved. Hello, are you getting my voice? Okay. So why I am telling that mutation uh, here, improving the solution quality is more, because here we are working more number of better solutions only now. After selection, what we got? More number of good quality solution and less number of poor quality solutions. Anyway, so that is the purpose of mutation. If we do some random changes in gene values, we expect that solution quality will be more. But again, believe that solution quality become less also. Okay, that is very normal. We cannot do anything. Now, which solution we are considering for mutation? I don't know. We are doing it randomly only. Randomly, we are picking some solution for mutation. Which solution we are considering for crossover? Do you have any control? Which solution we are considering for crossover? Do you have any control on that? No control. Again, we are thinking it randomly. Then why you are telling, okay, that probability of getting more better solutions is more. Why you are telling like that? Because we are doing everything after natural selection on. After natural selection, what happened? We have more number of better quality solution and less number of poor quality solution. So that's why you are telling after crossover and mutation, obviously there will be probability of getting good solutions will be more. And this is after we have completed mutation. Again, we are moving back to that, determine the fitness value of each and every individual. Now, can you tell me, once we are doing all these things, why you need to determine the fitness value? Initially, already you determine the fitness value only now for each and every solution. But again, we need to compute the fitness value because here the nature of the solution changed. Instead of CT10, we have added CT5. After the crossover, what happened? Solution structure, that means solution structure means position of parameters, position of cities in case of traveling salesman problem is changing or not? Yes, it is changing. That's why again you need to compute, the fitness value of each and every individual. Then again, same thing. Next generation, this we need to compute. So how much time you will compute it? When you will stop? Can you tell me here when you should stop here? This process, this flow chart, when you should stop? You can tell, sir, it is already written. If your number of generation is greater than 100, you should stop. But forget about that. Can you tell me any other criteria where we should stop here? This is our genetic algorithm. We are describing in terms of flowchart. So where we should stop? Can you tell any idea? Participants, those who are joining online, can anyone share when we should stop here? Forget about that. Here I have given, okay, if you cross maximum number of some generations is given 100, you should stop. Very good, very good, very good. So yeah, so online participants, can anyone share anything? When you should stop here? Online participants, please. You can type in chat box also. I think my scholars are also there. Devadas, are you there? Savanti, are you there? Hello. Anyway. So when you should stop actually correctly, what Sir has told very correctly. So what you should do? So see, so for each and every generation, what you are doing? For each and every generation, we are finding the average fitness value. Yes or not? First generation, we got average fitness value. It was something 30. Second generation, we got, it may be 40, 50, something else. So each and every generations, we are finding the average fitness value. Now, suppose once you are moving some generations and you are finding your average fitness value is not significantly changing, then what will happen? That means your solution has converged. You got the required solution. Average fitness value will be almost fixed. There will not be that much significant changes in the average fitness value once you are moving through the generations. Then probably you have got the solution, you should stop it. There is another significant stopping criteria for this genetic algorithm. Now, various issues involved in this genetic algorithm, that actually how to create chromosomes, what type of encoding to use, how to perform crossover and mutation. Okay, how to select parents for the crossover. So quickly here I will tell something how to create chromosomes. Actually, this is one of the biggest challenge for any this kind of genetic algorithm, or not only genetic algorithm, I should say that for any meta heuristics, it is the biggest challenge. Okay, how to create the initial population. And you should be, I should know one fact, that if your initial populations are good, then only there will be a maximum probability that you will get some solution. And if your initial population is not that much good, then it will be very much difficult to get the answer or to get the solutions. You know, today various research works are going on how to find out how to make the initial set of solution much more efficient. Because you see, meta-heuristics like genetic algorithm, it is working, it is based on the initial solutions only, na? Starting with the initial pool of solutions. Slowly you are updating the solution quality. So if your initial solutions are not that much good, then obviously you may not get that kind of good quality solution at the end. Now, again, you may think, sir, then how to find out good number of initial solutions? Then you need to apply some machine learning techniques, actually. You can apply K-means clustering, you can apply fuzzy C-means clustering, or other machine learning techniques you can apply to get the initial number of population. Recently, actually, we did some research work that we applied K-means clustering to find out the initial pool of solutions, and ultimately we found that our algorithm is giving a much more better result. Anyway, so what we are discussing, okay, how to create chromosomes. Now see, this is the binary representation and encoding of chromosome. See, your chromosome. So now binary means, as you know, 0, 1, 0, 1. So can you tell me why I am writing, or how many 0, 1s I should write here? Chromosome 1. Maybe, I don't know how many 0, 1s are there. Let us assume 20 numbers are there. So can you tell me what do you mean by 20? What will be the size of the chromosome? How to determine it? How many zeros and ones will be there? this 1 or 0, what does it mean? This is one gene only, na? First gene, second gene, third gene, fourth gene. 1, 0 means values of the genes only. So how many 0, 1 will be there? What will be the length? What will be the size of any chromosome? Actually, if you look to the traveling salesman problem, easily you can find out what will be the number of cities, that will be the size of chromosome. So, okay, so that in binary encoding technique, simply each and every chromosome we are representing using zeros and ones. Now, can you tell me, traveling salesman problem, can you represent using zeros and ones? Traveling salesman problem, can you represent using this binary encoding technique? This binary encoding technique is not helpful for each and every problem. For some specific problem only, binary encoding is helpful. Specific problem means what? Where each and every chromosome has two answers, either yes or no, either true or false, positive, negative. Then only you can apply this binary encoding technique. Otherwise, different encoding technique you need to apply. So I can tell one important problem that where you can apply this binary encoding technique. Or can you think of some problem where we can apply this binary encoding technique? Any problem where, do you know knapsack problem? Knapsack problem, important, very much important problem. I think it is important for computer science, mathematics both. Knapsack problem. Here we are keeping some items in a bag. Each and every item have some weight, associated values. Knapsack means one bag. So bag has the maximum capacity. If you are putting the item, what is your target? Our target is to maximize the value because each and every item associated with a weight as well as a value. We are keeping the items in a bag, knapsack. Bag has a maximum capacity, maybe 20-50 kgs. If you exceed the capacity, bag may be damaged. You cannot exceed the capacity. Now see, this is your optimization problem or not? So how to put the items in a bag? To maintain the weight, weight should not exceed as well as your value will be maximized. So this is called knapsack problem. So this kind of problem, can you represent using this binary encoding technique? Simply yes. Because what is the answer for each and every item? You can put the item in the bag, yes or no? So that means for knapsack kind of problem, you can represent using this binary encoding technique. So many other encoding techniques are there. So simply we'll avoid that. Now, how to determine the chromosome size? As I told, what will be the chromosome size for the knapsack problem? How many items you are keeping in the bags? Because now actually, as I told that, what will be the chromosome size for knapsack problem? What will be the number of cities? So traveling salesman problem, knapsack problem, how many items are there? Now, this is a population. See how mathematically or simply graphically we are representing the population. These are the various string. String means what? Chromosome. Chromosome means what? Solution. So we have a multiple number of solution in our initial population for this genetic algorithm. Now see that. Selection, how you will implement selection. This is another reproduction procedure. Selection. Selection means just check these two statements. More copies of good strings. String means what? Solution only. More copies of good strings, less copies of bad strings. As I told, meta heuristics which are working based on the based on the population. So population size will be fixed in each and every generation. If we started with 10 solution in the next generation, what will be our number of solutions? 10 only. Third generation, what should be our number of solution? 10 only. That means you can remember that one problem I told that where the fitness value was 50, in the next generation, you take it twice. 30, 20, 30, 40, take one time, but 50 you take twice. Why I told that? See, more copies to good strings. So which are good solution? You should skip more copies to the good solution and fewer copies to the bad strings or bad solution. This is natural selection only, na? Good solutions will have a higher probability to be selected. Poor quality solutions will have a less probability to be selected. But can I tell one poor solution has a zero probability to be selected? Can I tell one poor quality solution has a zero probability to be selected? I can never tell. Because each and every poor quality solution will have some non-zero probability to be selected. Zero means that they will not be selected at all, but that I can never tell because we are doing everything stochastically. We are applying randomness to our solutions, randomness to our procedure. We cannot tell. So each and every solution will have some non-zero probability to be selected. So this is the natural selection. Now few things are there, that is proportional selection, Rowley Wheel selection. That now here one important mathematics is there that I will come quickly. Will tell what is Rowley Wheel selection, natural selection. How technically we can implement this natural selection? Just check. Fit three solutions A, B, C. Solution A, fitness value 3, B 1, C 2. This is our wheel, Rowley wheel. Assign A. So how much portion it will occupy? 50%. B 17%, C 33%, it will occupy the wheel. Now take a point. Suppose here I am taking some point and you wheel the spin n times. Spin the wheels n times. Then what will happen? Spin the wheel 5 times. Which solution has a higher probability to be selected? Which solution will be selected? More number? A only. Which solution will be selected? Less number? B only. But can I tell B will never be selected? No. That I mentioned that each and every solution will have a non-zero probability to be selected. But which are the better solution? Higher probability to be selected, lower solutions, poor solutions, less probability to be selected. But at the same time, I should mention that it is non-zero probability. Each and every solution will have some non-zero probability to be selected. Now see, technically how we are implementing this natural selection. I told so many things regarding natural selections. Now technically how we are implementing it. Oh, few other things are there that I will skip. So actually tournament selection, this is another this natural selection mechanism. Simply I'll skip it. We'll skip everything. Elitist model of genetic algorithm. See here I will tell something. Now what is elitism or elitist model of this genetic algorithm? Now suppose let us assume we have 5 solutions at one population. And for one solution, I am telling 5 solutions we have. Solution 1, fitness value 10, 2, 20, 3, 30, 4, 40. Solution 5, fitness value is 500. Now see the situation. Solution 1, 10, 2, 20, 3, 30, 4, 40. Solution 5, 500. Fitness value is so high. Now, if we apply this high fitness value solution in crossover or mutation, what may happen? Higher solution, very much good solution, it will lose its fitness value. It may be damaging. So what we should do? A solution which have exceptional good fitness value, don't apply anything. Don't apply anything. Directly shift to the next generation. That is called elitism. Are you getting the fact? Solution number 5, fitness value exceptionally good, 500. If we apply crossover, mutation, what may happen? The solution may lose its fitness value. Then directly move the solution, directly shift the solution to the next generation without applying anything. That is called elitism, elitist model. Best string, best solution up to the current generation will be preserved. This is important for our convergence procedure. You are getting a very good solution. What may be? That solution is the final solution, na? Maybe. So why are necessarily to change it? Better to shift it directly to the next generation. That's why elitism or elitist model is very much important for genetic algorithm. Now, how to implement crossover? How to implement this mutation? What is crossover? See, crossover, partial exchange of information between two randomly selected parent chromosome. Partial exchange of information between two randomly selected parent chromosome. What you will do? Now let us check it here. Suppose this is my one chromosome, this is my second chromosome. Check it what you are doing here. We are applying crossover. So we are simply exchanging some information between two randomly selected chromosome. Exchanging some information or not. See the second part, taking from this and this. See here. Are you getting how we are exchanging the information here? How we are exchanging information between two randomly selected parent chromosomes. So this side, left side, first chromosome, second chromosome. How exchanging information in the right side? Are you getting right side? How we are getting? So this is our crossover actually. So this is called single point crossover. Now multiple number of crossovers are there, multiple types. It may be multiple point crossover, it may be uniform crossover. Many kind of crossovers are there, but this is one of the simplest crossover that is called single point crossover. Now see, if we apply binary encoding technique, if these two are chromosome 1, chromosome 2, now see, once you are applying crossover, we will get two offspring solutions. Just check it from here. From our chromosome 1, chromosome 2, we are getting two offsprings, offspring 1, offspring 2. What are the changes we are getting? Just check it. Simply here we are doing some exchange of information. Exchanging of information in the case of crossover. What is mutation? As I told, immediately after crossover, you should randomly select some chromosome and then randomly select some position, some gene, and then change the value of that gene. That is called mutation. Now see, suppose randomly selected offspring 1, randomly selected offspring 2, randomly selected some position, fourth number of position. What was the value? Value was 1. We have changed the value now. It is now 0. Here, what is the value of now? 0. Changing to 1. Here, 1. Changing to 0. After crossover, randomly select some chromosome, then randomly select some gene, then change the gene value. That is called mutation. So what you are expecting? We are expecting by randomly doing this kind of changes, our solution quality will be more. That is only our expectation in terms of mutation. Now here I should say two more things. One is exploration, second one is called exploitation. I will define it, then I will ask you some questions. What is exploration? Explore, diversification. We have some search space. We want to explore the search space. That is called exploration. Diversification. We are having some search space. Search space, what is there? Number of solutions are there. We are exploring. That means diversification. That means we are exploring the search space. We are searching through the search space as a maximum amount as possible. That is called exploration. Next one is exploitation, intensification. What is exploitation? Suppose in the search space, we are getting some solution at some point, which is much more better. Then what we should do? Recent past is the good indicator of near future. Normally we say recent past is a good indicator for your near future. That means once you are getting some good solution, what is your expectation? In the nearby areas, solution quality may be much more good. We are getting some solution some point. Nearby areas, if we fix ourselves, maybe solutions are much more higher, good quality actually. Okay, so that means intensification. So that once we should restrict ourselves. No, don't explore anything. Once you are getting some good solutions, be restrict yourself in the nearby solutions of that good solutions. There might be your better quality solution. Now see, so for in any meta-heuristics algorithm, initially where you should focus, exploration or exploitation? Exploration only. For any kind of meta-heuristics, initially we should focus on exploration. We need to traverse to the search space as maximum as possible. Then slowly what we should do? We need to reduce exploration. We need to increase exploitation. Because once you'll be traveling through the search space, automatically you'll be moving towards the good solution. Because what is happening? Your average fitness value is increasing only. That means automatically you'll be moving towards the better solution. That now, so initially you should focus on the exploration, then you should reduce exploration, you should maximize exploitation. In any of the meta heuristics, you should maintain a very good balance between exploration and exploitation actually. Almost all the meta-heuristics are suffering from this only. There is no proper balancing factor between exploration and exploitation. That's why almost all meta-heuristics, sometimes they are having some failures. Recently, gravitational search algorithm that was developed. And what the researchers are claiming in that GSA, gravitational search algorithm, exploration and exploitation is that much well balanced, simply it is outperforming all of our existing algorithms. Because in genetic algorithm, I don't know actually, whatever we are discussing, how we are balancing exploration and exploitation. I don't know how we are balancing here. No proper balancing factor is there for genetic algorithm. Now see, we discussed crossover and mutation. Can you tell what is the example of crossover? Exploration, exploitation, or mutation? What is it? Exploration, exploitation. Crossover, it is exploration or exploitation? Crossover is mainly for exploration. And mutation is mainly for exploitation. Okay, so here there is some actually what I should say, there is no proper balancing factor between exploration and exploitation. That's why it may suffer from that. Okay, so let us proceed. Yeah, mutation already I told. Yeah, some cross you see. Now, as I told, that crossover. So how many times you will implement crossover? How many times you implement mutation? Do you have any restriction on that? Do I need to apply crossover on the entire set of population? Or I should restrict myself? No, no. If you have 10 solutions, apply crossover only for 2, 3, 4, 5 solutions. Normally, what we are telling, crossover probability 0.7, mutation probability 0.2 to 0.3. Crossover probability you are taking more, mutation probability you are taking less. What is mutation probability? How many solutions you will consider for mutation? Will you apply? Will you consider all solutions for mutation? Will you do that? No. What will happen? If you consider all the solutions for mutation, then your average fitness value will be grammatically simply majorly degraded. Majorly it will be degraded. So mutation probability should be less only, where crossover probability should be more. But don't apply 100% crossover. No, no. What I told, some solutions may be good only now. Why you need to apply crossover unnecessarily? So crossover probability should be more than the mutation probability. Normally, what you are doing in your programming, 0.6 to 0.8, 0.2 to 0.3. That is the standard procedure. Normally, you are applying that. This is termination criteria already you have discussed many applications. So applications will not come. Now we'll come to our different topics. I hope that yes, 1 hour. So that means now perfectly you have set our background for this single objective optimization. So whatever we have discussed so far all belongs to this single objective optimization. What was your objective for traveling salesman problem? I am never telling go for both. Minimize the cost, maximize the benefit. I told only one thing. Either you should minimize the cost or go for maximize the benefit. Suppose from Vijayawada here, from your institute, I will travel to airport. I want to minimize the cost. I want to minimize my time. Is it possible right now? I want to minimize. So here both objectives. See, I am not working on a single objective. I am working on this both objective. So in our real life, what is happening? We are working on a single objective or we are working on multiple number of objective, multiple number of objective only. And at the same time, where we are finding the objectives are conflicting in nature. Objectives are very much conflicting. If I want to minimize the cost, here I am traveling from here to airport, minimize the cost, better I need to walk. Okay, then if I start walking, I don't know when I will reach there. So see the situation. So minimize the cost actually. So then what time is maximizing. So the conflicting only. I want to minimize the cost, then time will be maximized here. And okay, if you suppose uh, here again, I will show you some example for in your real life. Now, if you go for that, suppose, okay, another example I should tell in our real life, what will happen here. I will come to that part first, then we'll see. See, another example I will show you here. Here, now check this example. So this is the economy level and this is the time taking. Okay, so that means see. So if I start walking, this economy level, I am suppose I want to move from here to some other places. I have started walking. Time taken will be so much high, but economy level will be very much less. Okay, now see. I have taken some bicycle actually. Then what will happen? Now see. Time taken, it will be little bit less. This it will be from walking little bit less actually, but economy level again less only. Now this I have taken some flight from here to from this Vijayawada to Hyderabad. Then what will happen? Economy level will be more, but time taken will be less. Now see, all these are conflicting in nature. How do you make a proper balance? In our real life, whatever problems you are facing, see, all the objectives are conflicting in nature only. If you want to maximize one thing, that will minimize other thing. Like that, all are conflicting in nature only. So how to make a proper balance between these two objectives, these kind of situations? So for these kind of situations, we need to apply this multi-objective optimization techniques. Now, can you tell what will be your solution? I want to minimize the cost from here to Vijayawada airport. I want to visit, minimize the cost. I want to minimize my time also. Then what is the solution? I want to minimize my cost as well as I want to minimize my time. And I don't know, maybe from your institute, as I was listening, there are no Ola Uber, nothing is available maybe to move from here to Vijayawada airport. Then what to do? I should take some car. If I take some car, again the problem is the cost will be more, time will be less. Okay, I'll not take car. I'll take bike only. Then time maybe little bit more. Okay, cost little bit balancing. Now, so which solution I will prefer? See the situation. So which solution I will take? Which solution I'll be preparing here? Should I start walking? No, I should not start walking. That means, see, if sir, you please take a car. No, car I should not take. That is more costly. No cabs are available from here. Sir, you take bike. No, bike may be risky. Then should I stay here only? Your guest house is so much good. I can stay here only. anyway, that means now see the situation here. So that means for this multi-objective optimization problem, multiple number of solutions will exist. There is not a concept of single solution. I don't know which I will do. Okay, I will take a bike, I will take a car, or I'll take some of your faculty members to drop me. So what will happen actually? So which solution I will prefer? You say I'm very much confused about it actually. That means for any multi-objective optimization, there is no such concept of single solution. There will be multiple number of solutions. And you need to apply your problem domain knowledge. That means you need to find out which will be perfectly suited for you. Since now I am coming to deliver my talk, I am feeling car will be perfectly fitted to me. If I am coming personally, I feel that no, I'll catch Devanaran to take to pick up me from airport. See the situation. So that means what I am telling. That means so once we have a multiple number of solutions, that means which solution will be perfectly fitted for me. That I need to check. So for multi-objective optimization problem, you can never expect a single solution. Multiple number of solution will be your answer. And from your domain knowledge, you need to take some set of solutions. So multi-objective optimization, we are having multiple number of objectives, and often the objectives are conflicting in nature. So if the objectives are conflicting in nature, obviously, then the problem, I think, is giving to us some headache here. You need to buy some car. Again, this is given purely for experimentation purpose. So you can purchase this car or that car, but what will happen? In one car, comfort will be more, another comfort will be less. In one car, cost will be more, cost will be less. Now, which car will prefer? Both are the solutions actually. So based on our comfort level, you need to prefer to the car. Okay, so now see that once we started discussion regarding this multi-objective optimization, then what I should tell that you will forget about single objective optimization. But multi-objective concept is coming from single objective only. If you are having a strong background on this single objective, then only we can go for this multi-objective. So all the real life problems what you are facing that are multi-objective in nature only. Let us come to this part actually. So what will happen? I will show something. Okay. So suppose I have two things. One is bigger car as well as one is smaller car. See how interestingly how the solution I will get here. Bigger car and smaller car. For both this car, what I am finding economy level is same. Let us assume that economy level for both cars are similar. But time taken for bigger car is less, smaller car is more. So which solution you will prefer here? Obviously bigger car only, na? Both smaller and bigger economy level cost is your price, it will take same. But for bigger car, time taken is less. Smaller car, you are taking more time. So which solution you will prefer? Obviously, bigger car you will prefer. See that. We have two solutions, smaller and bigger. But these are multi-objective. Both objectives are here, conflicting in nature. Time and economy, it will conflict. But here you are selecting this bigger car actually. Now what is happening? Can you tell me what is happening technically here? See, my bigger car, it is better. My this solution. So let us say this is a solution. This solution is better with other solutions, at least for one objective. And this is not poor with respect to the other solutions for all other objectives. See what I am telling. This solution is better, at least for one objective. Yes, it is better or not. For objective time taken, it is better or not. This solution is better, at least for one objective. At least for one objective, it is better. But it is not poor for all other objectives. Is it poor for economy level objectives? No, it is same only. Then we will say, my this solution dominates that solution. Bigger car dominates the smaller car. You know, for this single objective optimization, the concept is that goodness of a solution. But in case of multi-objective optimization, concept is the dominance of a solution, degree of dominance or dominance degree. That means here my bigger car, it will dominate the smaller car. Okay, so I'll make it very much clear once again. Now let us come to the situation. Single objective and multi-objective. So single objective, how we'll find out? Betterness of a solution. So superiority of a solution we can find out using the objective function. And here the concept is the dominance. Here no objective function. Here the concept is all about this dominance. Goodness of a solution you can find out by applying the concept of dominance. Now slowly we will see that what is dominance actually. Let us try to understand what is dominance testing. See, two solutions we have taken. One is x1, second one is x2. When we will say x1 dominates x2, now see, x1 dominates x2. If solution x1, no, then x2 in what terms? While solution x1 is strictly better than x2, at least one objective. Exactly same thing you have seen in my last example. X1 is not poor than X2 in all objectives as well as X1 is strictly better than X2 in at least one objective. If this is the case, then we will tell X1 dominates X2. So X1 dominates X2 means what does it mean? X2 is dominated by X1. The similar thing. Let us tell you some quick example for that. See, solution 1 versus solution 2. Can I tell solution 1 dominates solution 2? Just check it. Can I tell solution 1 dominates solution 2? So if F1 maximization, F2 minimization. So solution 1 touches here this value. Solution 1 F2 that value. That side. For solution 2 this value and F2 axis that value. So which is better? Solution F1, solution 1 or solution 2? Solution 1 is better than solution 2 in terms of F1 as well as solution 1 is better than solution 2 in terms of F2. For both the objectives, solution 1 is better than solution 2. So, okay, perfectly. Solution 1 dominates solution 2. See the next case, 1 versus 5. 1 versus 5. So solution 1 or solution 5 dominates solution 1 in terms of F1. Solution 5 dominates solution 1 in terms of F1 objective. But for F2 objective, both are same. That means here solution 5 dominates solution 1 at least for one objective. That is F1. But solution 5 is not poor than solution 1 for the remaining objectives. Am I telling correctly? Solution 5 dominates solution 1 for at least one objective. But for all other objectives, solution 5 is not poor than that of solution 1. If this is the case, then tell it 5 dominates 1. Now check next. Solution 1 versus 4. Solution 1 versus 4. Solution 4 is better than solution 1 in terms of F1. 4 is better than 1. Solution 1 is better than solution 4 in terms of F2. So can you establish any dominance relationship between solution 1 and 4? We cannot establish any dominance relationship between solution 1 and 4. Neither solution dominates. We cannot show this. There is no domination relationship possible for that. So that I was telling the domination part. Now let me come to some, this is all the mathematics. Okay, now let us see. Non-dominated set of solutions. So once you are working with this multi-objective optimization, we should know what is the concept of non-dominated set of solutions. Now see, what is a non-dominated set? Given a set of solutions, non-dominated means the set of solutions that are not dominated by any member in that solution set. I'll show you some example. Non-dominated, name it itself, non-dominated. Non-dominated set of solutions are the set of solutions which are not dominated by any member in the solution space. I will tell. That I will show you some example. And this non-dominated set of solution is called Pareto-optimal set. And the boundary defined by this Pareto-optimal set is called Pareto-optimal front. Later I will show you using some example, then it will be maybe very, very much clear. Now quickly we'll come to this example. Suppose if you want to purchase some car, objective is speed. Okay, speed is more, we will purchase the car, let us say. Once speed will be more, then what will happen? Your riding comfort may be poor, handling maintenance may be poor, it may be expensive, it may be not that much fuel efficient, it may be unsafe. So should I purchase some car based on the criteria speed only? It is a single objective problem or it is a multi-objective optimization problem? Multi-objective only. We should not go for only speed. So we should consider each and everything actually. See, multi-objective, that means, see, speed should be okay, comfort should be okay, maintenance should be okay, price should be less. Fuel efficiency should be more, safety should be more. So this is purely a multi-objective optimization problem. So how to solve this kind of problem then? Are you getting it? Few objectives we need to maximize, while few other objectives we need to minimize, where those are simply conflicting in nature. So how to go for that? Here I will give you a good idea. See, these are the set of cards. Car mean what? Nothing but a solution only. So these are some set of solutions. Let us say these are the speeds. Okay. And here, see, I'm telling this is a population. Population means what? Set of solutions will be there. So these are some set of solutions. So this is speed and this is handling. Speed, and now check it. So if we go for speed, then what you will purchase? 70, maximum speed that you will purchase. If 70, then what your maintenance will be? Very much less. You don't want that. You don't want that. You want a balance. Okay, it is 30 only. We should not purchase it. Next. Okay, if handling is more, maintenance, that means good only. But again, speed is very less, 20. Who will purchase that? No one will purchase it. Now see the situation then. Then which solution you will prefer here? It is a very much difficult to find out some solution here. See, here I have plotted some graph here. So we are focusing on two objectives, objective 1 and objective 2, speed and handling. See, all these points I have graphically plotted. What about the solutions? A, B, C, D, E. I have graphically plotted these solutions. Okay. So x-axis speed, y-axis this handling. Now see what is happening here. Take it. So if we consider solution C, so solution C, so that means 10 with the speed, 40 with the handling. This is this side 10 x-axis, y-axis, you will find out 40. Let us check solution B. Solution B, see. So solution B will dominate solution C or not? Can you tell me? Solution B will dominate solution C or not? Yes, solution B will dominate solution C because solution B is better in terms of speed as well as in terms of handling. Both objective it is better, so it will dominate. Solution E, it will dominate solution C or not? Solution E, it will dominate solution C. Yes, it is dominating solution C. Solution A, it will dominate solution C or not? Yes, solution A also it will dominate solution C. Now, what about solution D? What about solution D? A very pathetic situation for solution D. Okay. So what will be our non-dominated set of solution here? That means, can you remove from our solution space solution C? C. That means out of these solutions, you can go for any solutions. These are called non-dominated set of solutions. Is it like that? B is dominated by E is dominated by B, D is dominated by A is dominated by D, and none other solution dominates each other. No solutions dominates each other. As well as here, in this solution space, no solutions are there which are dominating these solutions. Any solutions are there? Only one solution was there, C, we removed actually. So this is called non-dominated set of solutions, C. So this is our now answer. You will go for, you can purchase anything among A, B, D, E. C. How we are trying to find some solution here? As I told, multi-objective optimization, it will give you a multiple number of solutions which are non-dominated. You cannot define any dominance relationship between these set of among these set of solutions. So here you will getting some idea regarding this non-dominated set. Now, what I told you exactly, all these things are written here. This is mathematical definitions. So mathematical part I will avoid because here I think I'm very poor in mathematics, so better to skip it. Okay, so okay, scaffold study also will skip. So we'll come to some important part. Okay, we'll come to some important part here. Yes. So as I was mentioning that we are trying to now explore this multi-objective optimization. And this is a simple fact, how to compare single objective and multi-objective. Now, as I told that for this multi-objective, see, multi-objective solution, so we have two goals. One is convergence, second one is diversity. And for multi-objectives also, we will have multiple number of solutions. Okay, in single objective, you may have only one solution as the final answer. But in multi-objective solution, you will have multiple number of solutions at the final answer, as well as multiple number of conflicting objectives also will be there. Now, these are the two goals for this multi-objective optimization. One is convergence, second one is diversity. What do you mean by convergence? How you are coming towards that Pareto optimal front. What I told, what is Pareto optimal front? In Pareto optimal front, some set of Pareto optimal solutions are there. What I told, what are those Pareto optimal solutions? Pareto optimal solution means those are nothing but the non-dominated set of solutions. So what is our target in case of multi-objective optimizations? We need to find out the non-dominated set of solutions. And where are the non-dominated set of solutions? Those are in the Pareto optimal front only. So here we will see. Now see. So this is our Pareto optimal front. This is we want to minimize F1 as well as we want to minimize F2. Both the objective we want to minimize. If you want to minimize both the objective, then that may be our Pareto optimal front. Now see, in Pareto-optimal front means this is the boundary, this is the region. And in Pareto-optimal front, there are some set of Pareto-optimal solutions. Pareto-optimal solutions are nothing but non-dominated set of solutions. Whatever all these black circles are there, can you tell this circle is dominated by this circle or this one is dominated by this? We cannot tell. We cannot define any domination relationship among the solutions which are there in this non-dominated set of solutions. Whether I can tell non-dominated set of solutions, they will dominate all other solutions. These yellow color solutions are dominated by these black color solutions or not? Yes, only. Because this is minimization. We want to minimize x-axis as well as we want to minimize y. F1, F2, both we want to minimize. So this black color solutions is dominating this yellow color solutions. Okay, so what should be our target? So this is our feasible solution space, this region we are getting. This is our feasible solution space. What is our target? Our target is to find the solutions which are as closer as possible to this true Pareto optimal front. That this I am telling, this is my true Pareto optimal front. What does it mean? This is ideal solution. Ideal means best solution. But what I told earlier, none of the optimization techniques will give you the guarantee that it will yield some best quality solution. No, you can never do that. None of the optimization techniques will give you the guarantee that it will provide you some best solution. But why? What it will give you the guarantee? It will give you the guarantee that, okay, it will produce some better quality solutions, which are pretty much closer to the best solution. So what is your target? Our target is to reach as closer as possible to this true Pareto optimal front. Are you getting the point or not? True Pareto optimal front means what? Best solution. But none of the optimization techniques will give you the guarantee to get the best solution. So what should be your target? To come as closer as possible to this true Pareto optimal front. This front. We want to come as closer as possible. So this is convergence. What is diversity? We want that. The which are the solutions? That solutions should be well diversed, widespread throughout this Pareto optimal front. That means if I get some set of solution only here, some cluster of solutions only here, that is not a good solution. Whatever solutions you are getting, that will cover approximately the true Pareto optimal front. It should be widespread. It should be widespread from this side to this side, so that we can select our own solution based on our domain knowledge. It should not be clustered in one place. It should not be grouped together in one place. It should be widespread throughout this Pareto optimal front. So that's why I am writing here convergence to the true Pareto optimal front as closer as possible, well diverse. That means cover the whole spectrum of this Pareto optimal front. So these two are the objectives for any multi-objective optimization. Now see here, which are the bad solutions, which are the better solutions, which is true Pareto optimal front. So this line, this is our true Pareto optimal front. Obviously, this is our better solutions as closer as possible. This is not that much better. So see, sometimes these are clustered in one group only. Here it is grouping, making this is one group, this is another group. So this is clustered, this is not well diversed. As well as red color solutions are not closer to this true Pareto optimal front. We will say, okay, so this is our better solution. So this is some ideas that you need to follow. So that once again I am writing converge on the Pareto optimal front, maintain diversity as much as possible. So are you getting what should be our objective for this multi-objective optimization? So its solution should be well diversed. Firstly, secondly, it should be as close as possible to this true Pareto optimal front. Now, these are few well-known multi-objective optimization algorithms starting from NSG well-known. So today mainly I will discuss number 2. This is non-dominated sorting genetic algorithm. So actually that was proposed by Yeah, that was proposed by Professor Kullan Moedev. So as you know that Professor Kullan Moedev is very much well known for his contribution in this multi-objective optimization field particularly. So Sir only written actually this algorithm, this NSGA2, this fast elitist mechanism. So now today mainly we'll try to highlight this algorithm only NSGA2 as well as if time permits, we'll find out some research objectives. Now see, so this particular algorithm, how many citations it is getting? So those who are working on this multi-objective optimization, this is the must read paper for them. We need to read this paper. We cannot do anything. That's why this paper is getting that much citations. Actually, this data I captured, I think 5 years back. I need to update it. Maybe now it is 60,000. So now you can find out what is the importance of this particular algorithm. We cannot do anything if you don't know this algorithm in multi-objective optimization. Now see, where is the difference between single objective and multi-objective optimization? This flowchart will give you the difference. Difference between single objective and multi-objective. You have seen the flowchart for single objective. Can you find out what is the difference between my earlier flowchart and this flowchart? Where is the difference? If you look closely, so here I have only added one extra block, environmental selection. The remaining all things are similar. Only one block I have added extra, that is environmental selection in this multi-objective optimization. Remaining things are exactly similar to my single objective optimization. So, okay, let us focus on this. What is environmental selection and how it is contributing to this multi-objective optimization? Now see, t equal to 0. So at the initial iteration, so we are considering P0 of size n. What is P0? Solution only, parent solutions. P0 means parent solution of size n. We are considering. Okay. Next. From this P0, we are getting Q0. What is Q0? Offspring solutions of size n. Okay. So from P0, how we are getting Q0? Using selection, crossover, and mutation. That's why initially I told all these three things: selection, crossover, and mutation. Okay. So P0, set of solutions, Q0, size n. From P0, we are getting U0. Okay, by applying simply genetic algorithm concept, natural selection, crossover, mutation. Next, what we are doing next? Yeah, R0, P0, and Q0. So we are combining. P0 means parent solution, Q0 means offspring solutions. We are combining parents plus offsprings. So what is your size now? Solution size 2n, n plus n, 2n. And we are finding R0. Okay, combining P0 and Q0. Okay. Next, see, you need to apply this environmental selection. What should be your objective? I will discuss all these things in detail. Environmental selection. What is your objective here? We need to find best n solutions from this set of 2n solutions. Initially, we have P0, size n. From P0, apply genetic algorithm concept, selection, crossover, mutation, you will get Q0. Add P0, Q0, you will get R0. What I am telling, from R0, our objective is to find out the best n solutions from the set of 2n solutions. Now, how will do that? For the purpose, we need to apply this environmental selection. Exactly what it is doing, that I will tell. Two things we are applying. First, non-dominated sorting, that is for convergent purpose. Crowding distance sorting, that is for diversity purpose. I will explain everything. So we are coming to the next iteration, t equal to t plus 1. Next, we are getting another set of parent solution. How it is getting? PT. Because from this 2n, what you got? N solution only. What is N solution? Nothing but PT. We are getting PT. So next, what should be your target? From PT, you will get QT. How you will get QT? Same procedure. Next, again go for RT. This PT and QT. Next. See, you should repeat it. Now see, so this is the flowchart for this NSGA2. Okay, non-dominated sorting genetic algorithm version 2. So that is the flowchart for that. Okay, now let me explain it very clearly. So we got size 2n from 2n, what we got here? First best n solutions, and then those n solutions we are becoming considering as parent. Again apply crossover mutation selection, getting QT. Again add these two things, PT plus QT, getting RT. Again go for applying environmental selection. So this process you should repeat until unless you are converging. Now see the situation. Initially you had PT, n number of solutions, then from PT what you got? QT. Next, check it very carefully what I am doing. So PT plus QT. That means now you have n plus n to a number of solutions. Then see, we need to apply this fast non-dominated sorting. Check what I told. Two things. Environmental selection. One is fast non-dominated sorting. Second one is crowding distance. So here, once we are applying fast non-dominated sorting, what it is giving? It is giving some set of fronts, F1, F2, some set of fronts it is giving. Check some set of fronts it is giving. Now, if you take summation of all solutions in those fronts, what will be the size? 2n will be the size. Got it? So if I take summation of all solutions, obviously here 2n will be the size. So what is there in front 1? Some set of solutions. What is there in front 2? Again, some set of solutions. Now, how we are dividing in various fronts? What is the mechanism? Obviously, that we will discuss. So from here, we are getting, if we take summation of all the fronts, we will get 2n. What is your objective? From this 2n, we will get only n solutions. Now see, if I take directly F1 to see what is happening, just check it clearly. So I am considering F1, putting it here. Okay, less than n. F1, putting it here, less than n. F2, putting it here. What is the size? Right now, less than equal to n, putting F3. Can you put F3 here? No, you cannot put F3 here. If you put F3, then what will happen? It will exceed the size n. Then what you should do then? Are you getting the point? You cannot put X3. You cannot put F3 here. So if you put F3, then the size will exceed n. What was our target? From this to n, we want to make it n only. If you put X3, F3, size will be more. So what we should do? Then you need to apply the crowding distance mechanism, crowding distance sorting. What crowding distance will do? So crowding distance, what it will do? Just check. So what about the set of elements we have in this front F3? It will sort it. It will sort it. All the elements, whatever we have in F3, and it will put the required elements here to fit the size to n. And remaining elements, what it will do? It will discard. Are you getting? From front 3, it will sort the elements. Okay. So it will sort the elements from better quality to poor quality. That means after doing the sorting, these remaining solutions it will put here so that the size should be n. And what about the rest solutions? Simply it will be rejected. Now, are you getting what is the requirement for this crowding distance? So crowding distance will apply in a particular front. Okay. To make some ordering of those solutions in that front so that better solutions we can keep accordingly to make the size n here. So that is our target for this crowding distance mechanism. So now we are getting n. So what is here? This is PT plus 1. So this, what about the other solutions? Simply we are rejecting. So from here, I think one very common concept or common idea we can think of. Now, can you tell me that which solutions are better? F1 front solution or F6 front solutions? Which solutions are better? What is our common idea regarding it? Solutions which residing in front 1, that is better, or residing in front 6, that is better? Which are better? Or how to make a ordering of all those fronts, F1, F2, F3, F4, F5, F6? How to make an ordering? Obviously, solutions which are residing in front 1 are much more better than front 2. Then only we consider in here only, na? Otherwise, how will consider here? What I told, from this set of 2n solution, we need to consider here n best solutions. Here it was 2n number of solutions. Here we will consider n best solutions from this set of 2n solutions. So obviously F1 is better than F2, F2 is better than F3, F3 is better than F4, F4 is better than F5 and so on. So this is an ordering. Solutions which are in the first front, that is better that of second front. Solutions which are there in second front, that is better than that of third front. That is our concept only now. To put the first n solution, not first n, to put the best n solution in this block. So F1 is better than F2, F2 is better than F3, and so on. That's why initially we kept F1, then we kept F2, then we kept F3. But once we are keeping F3, we failed some problem. How we solved the problem? From F3, we selected the best solutions, kept it in that block to make the size adjusted to n only. Remaining solutions from here, we discarded. And obviously, solutions from F4, F5, F6, we rejected. Now see, so importantly, just try to see this visual presentation, a graphical presentation, then you will get to know everything regarding this fast non-dominated sort. All these mainly theoretical ideas, but what are the Python programming behind that? As you know, today I have one more session, evening. So that time I will explain the algorithm as well as the Python programming behind this multi-objective optimization. We'll take some problem, two objective problem, and how to solve this problem using exactly the theory, whatever I am telling, we'll implement it using Python programming in our evening session. Okay, so this is our first non-dominated sorting. Let us see how it is working. So this is solutions from PT. What is the size? N only. From PT, whatever you will get. How many solutions are here? 4 solutions are here. From PT, whatever you will get? QT. How many solutions are there in QT? 4 solutions. So 4 plus 4, you are getting 8. What is your target? Best 4 to select. Okay, next see. So for the sake of simplicity, giving some number to the solutions, 1, 2, 3, 4, all these things. Next. Just check it. What we are doing here. Actually, you are applying this non-domination concept here. Just check. Consider this is a minimization problem. Minimization problem. Consider it. Okay. Now check. So solution one. Solution one. If it is a minimization problem. So which solutions are dominated by solution one? From my graphical presentation, is it clear? Solution one dominates 5, 4, 8, 7, 3. Take it. This is a minimization problem. Which solutions are dominated by solution one? Minimization. Both x, 6, it is not completely taking, that's why you have not considered 6. Okay, so now see the situation, how it is, how it is coming, see. So this dominates all these things. Minimization problem. Already we have seen how x1 will dominate x2. If you can remember that concept, what I discussed, how x1 dominating x2. That you told now, when one solution will dominate the second solution. If for one objective, it is strictly better, and for all other objectives, at least it is not poor. Then we told one solution dominates second one. One dominates all these solutions from that idea. And in reverse manner, what we can tell? 5, 4, 8, 7, 3 dominated by this solution 1. Okay, solution 1 dominates all these things. So we are keeping S1 equal to 3, 4, 5, 7, 8 there. How many solution dominates 1? How many solution dominates 1? No solution. N1 equal to 0. Just take it very clearly. So next, for each and every solution, you need to do that. For solution 2, minimization problem. Solution 2, how many solution dominates solution, how many solution is dominated by this solution 2? Minimization. So if you take this graph, obviously 3 and 7 will be dominated by this 2. So write S2 equal to 3, 7. So those two solutions dominated by 2. How many solution dominates 2? No. So it is 0. Next. Each and every case we need to find out. For 3, how many solutions are dominated by 3? Blank, nil. How many solution dominates 3? This 1, 6 and 2. That's why I have kept, that is 3. So remaining things we need to do in this manner. S4 dominates nothing. How many solution dominates S4? 4 solution. Next. 5. It dominates 4 and dominated by 1. That's why writing 4, 1. Next. 6. What is happening for 6? This 4, 8, 7, 3. This dominated by S6. How many dominates it? 0. So similarly for all other things, we need to do that. We are doing for every solutions. Next, now see here what we are getting here. Take it. For which of the solution domination count is 0? Solution number S1, S2 and this S6. What does it mean? None of the solution in the solution sets dominates these 3 solutions. That means this is our first non-dominated front. Are you getting? This is your first non-dominated front. How we are getting? First non-dominated front. None of the solutions in the solution set dominates these 3 solutions. That's why domination count is 0 only now. So these 3 solutions will belong to our non-dominated, first non-dominated set. Now what you need to do? For each and every solution in the first front, for each and every solution in the first front, we need to do the same thing. That means for each and every solution in the first front, solution 1 is in the first front, solution 6, solution 2. What you should do? Each and every solution for solution 1, we need to check how many solution it is dominating. 5, 4, 8, 7, 3. To which solution it is dominating? Reduce their counter by 1. Okay? Which solution? 5, 4, 8, 7, 3. This 5, 4, 8, 7, 3. So reduce their domination counter by 1. For each and every solution, you need to continue the same process. For solution 6, do the same thing. Solution 6. So that means 8, 4, 7, 3. 8, 4, 7, 3. Reduce their domination counter by 1. Next, for 2. For 2, again the same thing. For 2, 7, 3. Reduce their domination counter by 1. Now see. Now we'll get some new set of solutions. Their domination counter is becoming 0. So put them in the second front. Are you getting? So putting them in the second front. This 3, 5 and 8. Putting them in the second front. Now see. Now easily you can check. So which solutions are better? First front or second front? First front only it is better than the second front solutions. Next. For the second front solutions, you need to repeat the same process. So repeat the same process. Repeat the same process. I am not doing it as repeating it. Repeat the same process. Okay. Once you are repeating the same process, what you will get? You will get third front. Now see here. So we have applied fast non-dominated sorting. Once you have applied fast non-dominated sorting, what you are getting? You are getting some set of fronts where first front is better than second, second is better than third, and so on. So fronts we are getting, okay? So fronts we are getting, okay? So this is the algorithm behind that. This algorithm right now I will explain. So I will explain this algorithm once we will take hands-on session. Exactly the same algorithm we will implement using Python programming. So fast non-dominated sort is over. Then what you need to do? We are getting some fronts. If you take summation of all front elements, what it will be the value? 2n only. So from 2n, we need to select first n best solution. So here, these are the fronts, okay? all fronts. If we take summation, obviously we get 2n number of solution. Now see what to do. We need to find out, we need to implement sorting among the solutions within a particular front. We will consider one front and we will select which solutions are better in that particular front. What we will do. So this is a particular process. So I'll show you that. See. So how to check what is the crowding distance value of this solution? What I am telling, we need to find out the crowding distance value of each and every solution. Crowding distance value we need to find out for each and every solution. And based on this crowding distance value, we need to sort the solution from better to worse. We need to find out crowding distance for each and every solution. Here I have a mechanism for that actually. Now see. What I am telling, avoid the crowd. That means for if some particular solutions, if I find it is crowded, so this solution, avoid the crowd actually, this solution and this solution. I am telling here crowding distance is less. And some other solution, crowding distance will be more. Now check the solution here. Crowding distance less here for this two extreme end solution. What you are considering? Crowding distance is infinite. Why crowding distance is infinite? Because in this side we are not getting any solutions. That side we are not getting any solutions. Crowding distance is infinite. What is our target? We need to avoid the crowd. Why to avoid the crowd? You can remind that what I told initially well distributed. It should be well diversed throughout the Pareto-optimal spectrum. So that is our requirement that you need to go for this crowding distance. Now see here. So which are much more crowded? We are simply removing that, removing those solutions. These things we are removing. And remaining things we are keeping. That means okay. I will show you some mechanism how to find out the crowding distance solution. Now tell me when to find out the crowding distance solution. When actually? So initially you are finding some fronts. What you are telling? Front one element are better than front two. Front two is better than front three. Front three is better than front four, like that. When to find crowding distance? If you want to compare the elements within one front, then only you need to find out the crowding distance. In one front, we need to compare the elements that is necessary to find out the crowding distance. Here we will tell, I have some mathematical compute. Here I will explain later. Now see here. Actually, so this is the mechanism for finding the crowding distance. Just check how we are finding the crowding distance. Check. So all these elements A, B, D, F in the first front, how we are finding the crowding distance. Check. So A, crowding distance is infinity. Extreme end F, crowding distance is infinity. Remaining elements C, D, B, C, D, D, how we are finding crowding distance B. See, what is the mechanism? Crowding distance B, how we are finding? You see, 4 minus 2 divided by 6 minus 2, how it is coming actually. So this is coming from this example, just check. So we need to compute the fitness value, earlier solution and previous one. Earlier one, this like that, both the sides. So if this is the case, we need to find out the fitness crowding distance of B. Then you need to consider the value for A and D, which is the previous, which is next. A is previous to B, D is next to B. So we need to consider, once you are finding for B, we need to consider the solutions A and D. Now check. 4 minus 2. So you can check for D. This time is 2. What is time and cost? Objective. Time is one objective, cost is second objective. So 4 minus 2. 6 minus 2. What is 6? Just check. 6 means maximum. F time max, F time x max is equal to 6. That means for this objective time, which is the maximum value? Maximum value is 6. So this maximum minus minimum here, this is one is previous, one is next. See, 4 for B, D and A, check. D4, A2, that means for B. D minus A, fitness of D, fitness of A in terms of this time. And here, maximum fitness minus minimum fitness. This is for the objective time. Similarly, you need to do it for the other objective cost. 7.5 minus 5, check. A is 7.5, D is 5. Next, 7.5 minus 4.5. What is maximum value for the cost objective? 7.5. What is minimum value for the cost objective? 4.5. So 7.5 minus minimum 5 equal to this. So this is the mechanism basically, how we will find out the crowding distance for each and every solution. So crowding distance of B is this and crowding distance of D is this. And here I have written, so that is actually the mathematically, this is the algorithm behind the crowding distance mechanism. So now I am avoiding it. We are explaining at right time during our next session. So this is the way to find out the crowding distance. Okay. Now almost we are getting the fact that how to find out this non-dominated sorting as well as how to find out this crowding distance. Now how to rank two solutions? See, how to rank two solutions. We want to rank two solutions. Then what you need to consider? First, you need to find out in which front they are. Suppose we want to compare two solutions which are there in two fronts. So how to compare these two solutions? If they belong to different fronts, then easily you can compare. First front will be good than the second front. If they are in similar front, then how to compare? Then you need to come for this crowding distance mechanism. If only rank of those two solutions are same. Rank same means what? Rank same means they are in the similar front. In one front, similar front, then you need to go for this crowding distance mechanism. Where crowding distance is more, solution is much more better. Why? Crowding distance is more. That means no more solutions are there nearby to that particular solutions. Obviously, you will go for that. Now see what I explained. So this is the main loop actually. Initially, we went for RT, P2 union QT. Next, what we did? First non-dominated sorting we did. Next, once we generated first non-dominated sort, what we got? We'll got all these non-dominated fronts. Then what we did? See, we applied crowding distance mechanism for each and every front element. Then see, PT plus 1 union Fi. That means what you are doing? Each and every front, you are trying to add to some parent. What is the parent size? N. Front, we are adding to some parent. So how much time we will add? See, while PT plus 1 plus front element less than equal to N, we are taking the front elements, adding to the parents. How much time we will add? Until unless the size is less than equal to N. Now, once we are adding, if size beyond size exceeds N, then what will happen? If size exceeds N, then see. Then we need to sort these front elements. Then after sorting, what you need to do? What is the remaining element? N minus Pt plus 1. What is the remaining elements from this front? That front only will add to Pt plus 1. Try to visualize the situations. We are adding front elements to the parents. How much time we will add? Until unless size is less than equal to N. Okay, and if it is crossing N, then what you need to do? Then we need to find out the crowding distance. We need to do the sorting of these front elements and only best element from this particular front. Okay, we will add to Pt plus 1 by satisfying this. The remaining elements only you need to add this particular front. Now I think here now the concept will be very much clear actually. If I come to this diagram already you know. Now if I come to this diagram, this I will explain later. So this diagram, now just check it. This is our PT, this is our QT. What is the size? 2n. We divided into some front 1, front 2, front 3 like that. Here if we take summation of all front element, what is the size? 2n. What is our target? From this 2n, we want to find out the base 10 and we will put it here in PT plus 1. How to do that? Which is better, F1, F2 or F3? F1 is better. So F1 directly shifting to PT plus 1. Next, F2. If we put all element of F1 to PT plus 1, size will be less than n. Next, if we put F2 Pt plus 1, size will be less than equal to n. If we put F3 to this, size may be. If we put all the elements from F3 to Pt plus 1, size will be greater than 1. Then what we should do? Then we need to implement crowding distance sorting for these front elements F3. Okay, we will apply crowding distance sorting. So based on crowding distance sorting, we will get to know the fitness or dominance of each and every solution. Crowding distance of each and every solution we will know here. Then accordingly, what is the remaining elements? So that remaining elements we will take from F3 and we will put it here. So size will become here n. And waste elements we will discard. I hope now it is very much clear that how we are applying non-dominated sorting and crowding missed distance for the purpose of implementing this environmental selection mechanism. So this is our main loop actually. This is our main programming for this NSGA2. So here you will get to know firstly RT, P2, QT. You are divided applying first non-dominated sort. You are getting some front elements. Then we are taking the front elements, putting into PT plus 1. How much time we will put? Until unless size is less than equal to n. Now, if some cases size is more than n, then we need to sort that front elements, applying crowding distance. Then remaining element from this front. Only front I, check it, only front I only, we applied crowding distance mechanism. That means which are the better solutions from front I? So that elements we will put to PT plus 1 so that n minus pt plus 1, because initially what was the size of pt plus 1? It is n. We have kept some element. That means what is the remaining number of elements required? N minus pt plus 1. So that much elements only will keep from fi to pt plus 1. So that our now sizes of this pt plus 1 will be n only. This is the main mechanism actually. You need to understand, otherwise you cannot implement this NSGA2. But then what is our QT plus 1? From PT plus 1, we will apply genetic algorithm mechanism. Crossover, selection, mutation. We will get QT plus 1. Now this is our advantage actually. So actually what we do it here, see, a diversity among non-dominated solution is maintained using the crowding distance procedure. See, no extra diversity control is needed. Check it here. How we are maintaining the diversity in case of this NSGA2 algorithm. We are applying non-diversity of non-dominated solutions. We are applying using crowding distance mechanism. This is the new concept applied in this NSGA2, crowding distance mechanism. Easily you can find out what is the importance of the crowding distance mechanism. What was our objective? To converge towards the true Pareto optimal front, first objective. What was our second objective? To well diverge through the X spectrum. That was our second objective. So how we are maintaining the diversity along the spectrum? To maintain it, we need this crowding distance mechanism. And also we're implementing elitism here. Now I think this is 12 o'clock, exactly at right time we concluded. So I want to acknowledge my guide, Professor Tandrapal from Department of Computer Science and IIT Durgapur for providing me the knowledge on this NSGA2. As well as I want to thank to my guide, Professor Samorjit Kaur from NIT Durgapur for sharing his valuable knowledge to gain some knowledge in this NSGA2. Now this is some references that Kullan Moidev, as I told, that Kullan Moidev, if you go through this paper, only then we can understand something. This is a huge importance one. And needless to say that what is the applicability of this multi-objective optimization? As you know, once today, the first 1 hour I took for single objective, second 1 hour I took for this multi-objective. Again, 2.5 hours is left in the evening. So there we will discuss all implementation details. I will take one by one algorithm. I will take NSGA2 algorithm. I will take fast non-dominated sorting. I will take crowding distance. We will discuss in detail how to implement using Python programming. I will take some example that is two objective programming. Then we'll see. Probably if you attend evening session, then all these things will be much more clear. Today, mostly I highlighted a theoretical part. Intentionally, I have not discussed anything on this implementation part because evening session only will be coming to that part. Now, thanks to listen to me. But I think last more than 2 hours. As you know, this is my email ID as well as this is my phone number and WhatsApp number. So if you some quick questions you can ask. Otherwise, you are my colleagues only, most of you, and few students or scholars are also here. So please feel free to drop me email and also call me or WhatsApp me in this number. If you are interested to do some collaborative work in maybe artificial intelligence, machine learning, or multi-objective optimization, maybe on uncertain decision making, so please feel free to contact us so that we will feel happy if we get some collaboration from this Vignan University. So once again, I want to thank all the participants as well as those who are joining online as well as offline. Also, I want to thank my sincere thanks, convey my sincere thanks to that coordinators of this FDP, our 1 week faculty development program, innovations in machine learning, artificial intelligence, data science, and modeling. So I got a few emails from some faculty members regarding the invitation. So I'm really thankful to them. And particularly, I want to express my heartfelt thanks to Professor Devanarayan for keeping in touch with me and perhaps insisting me that, sir, please come here and to take this session in offline mode. Otherwise, I told that I'm very much busy. Probably I will not come. I'll take this session in online mode only. But due to his insistence to me, I came here and really I'm enjoying here the scenarios or all these things. I felt very good here. Uh, Anyway, so thanks to everyone. So if you have any quick questions, online participants, do you have any questions? Please type your questions or raise your questions. Online participants, please type it in chat box.
Sir, sir, what you delivered, it is very helpful to real life.
Yes, thank you.
So, is it NSJ2 is applicable in market nowadays?
Yes, so this is, see, so NSJ3 is also there actually. So what I discuss NSJ2 actually, so this is the most fundamental one. Many improvements are there over NSJ2. So yes, so multi-objective optimization is applicable for anywhere. We have done so many research works on multi-objective optimization. And what I will suggest that not only use multi-objective optimization as well as you need to apply some machine learning algorithms with this also. Today, what is the research trend? Either you need to apply optimization techniques in machine learning or you need to apply machine learning in optimization techniques. Application of optimization techniques in machine learning or application of machine learning tools in optimization techniques. So these two are very much, I think, emerging research directions. Simply using multi-objective optimization, it may be very much difficult for us. But if you go for this hybridization, then I think that will be some fruitful research work. But yes, what you are asking easily, we can apply it anywhere. An IPL scheduling problem, is a very much well-known problem. IPL, so many teams are there, visiting various cities. You can feel so many constraints are there. So if you apply multi-objective optimization for this IPL scheduling, now you can feel how they will be benefited.
Sir, normal small things means anyhow you will go to a shop means they will confuse. It is good, it is not bad means so many things. Suppose you will go a potato shop, they will say it is 30 rupees, it is 40 rupees, it will 50 rupees. We will use a equilibrium point. That means suppose in F1 axis or F2 axis, we are using the average and average. It will be better. 20, 30, 40 means 30 will be better for us. 99% case we are using 30 will be better. So is it a clear-cut solution for non-dominating?
Yes. So whatever you told, 30, that means yes. So that means 30 is, I think, dominating 20 and 40. Yes. That means here we will not get any single solution. No single solution you will get. Maybe 20, 30, 40, 50. Then here 30 and 40, dominating 20 and 50. So you'll go for 20 and 30. And if my capacity is more, I will go for 30. If someone capacity is less, they will go for 20.
5% is there.
Yeah. So that's why I told that once multi-objective optimization will give you set of solutions, then it should be our domain knowledge. From that domain knowledge, we should select our own solutions because multiple number of solutions will be there.
Sir, except elitism,
yes,
anyone is there for going to the next generation?
No, whatever concept I have knowledge so far, I have so far the knowledge regarding elitism only, although there is much more improvements on elitism.
Now you said cumulative is there. Suppose you are traveling salesman problem you are considering. You said cumulative is there.
No, cumulative what I told, that is for cost only. to find out the fitness value.
Hmm.
If we take one solution from TSP, what will be the fitness value or objective function value of TSP? Then perhaps you can take the summation of all the cost of all the edges, various cities they are connecting. Then that will be the cost. That is the fitness function only what I told. But elitism, obviously, actually, what I told, I did not say anything. Very few things I told regarding elitism. But itself, there is a huge number of research work on elitism. How to implement elitism actually once you are solving some problem.
Sir, one online question from Savanti Gola. Is
Yes,
the Pareto function always a continuous curve or discrete?
Okay. So, hello, Sravanti. Can you listen me? Hello? 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 Okay, so what I should do, so say actually, so if you are solving, your problem may be of two types. It may be discrete optimization, it may be continuous also. So what I have shown right now. So whatever I have, yeah. Yeah, already I have shared my email ID. I think once again I will.
Upper one, sir.
Only once again I will share, yes. So now if you are working on this discrete problem, discrete optimization, then obviously it will be discrete one. But if you are working on this time series kind of problem, so it is continuous in nature. Actually, two types of things are there. One is continuous, second one is discrete. Here, whatever I have shown, that is a purely example of discrete. But yes, that can be possible for continuous spectrum also. Whatever I have not shown it today, but yeah, you can contact me so that, yeah. How effectively crowding distance mechanism work for high dimensional problem? Yes, actually, for high dimensional problem, you know that you have some huge data set, big amount of data. So firstly, I think I suggest you that if you are working on high dimensional problem, firstly, use some machine learning technique to reduce your dimension. So that our problem should become feasible for us so that we can solve the problem. And obviously, then what would be your number of objectives? And as you know that if your number of objectives are more, then your crowding distance mechanism is going to be more complex. Because as you have seen in the example, that it is have a computational procedure which you need to apply for each and every objectives. So if objectives are more, that means your crowding distance mechanism is going to be complex. And ultimately, it will take some more time complexity because for each and every solution and for each and every objectives, you need to compute this crowding distance. So what we do actually, so normally if we feel that our number of objectives are more, so then we will try to reduce the number of objectives to maybe some 2, 3, 4, so that our problem, what are our solution procedure, that will become effective one. Any other? Anyway, Sravanti, so I hope that you got the answers, but really that's a very good questions. Again, if you have anything, so we can discuss later. Okay, so already I have shared my email ID and contact number. So I think you can take it from there. Okay, so that I think if there is no other questions, we will close it. So evening or again, we have some sessions. So please note down your questions if you have something so that evening I can answer. Okay, thanks. Okay, so thank you once again for sharing your valuable time with me. So thanks, everyone.
Thank you, sir, for continuous 2 hours talk. And most important thing, the title. So whatever words are involved in the content, everything it is explained clearly from student to last one researcher. So actually, when the person's researchers delivering any content, domain knowledge is very, very important. In this session, sir explained each and every basic key important terms from bottom level to top level. Domain knowledge is very important because we are applying these concepts in application orientation, and explanation of the genetical algorithms and construction of the models, everything sir explained very well. So linkage between the theory part and application part, both are very important. In this talk, what I observed, the most key important points: what, why, how. These points, asking the questions are very simple, but answering the questions to these three words very difficult. I thought, and my participants also enjoyed receiving the answers from these type of questions. Thank you, sir. Thank you for your valuable lecture. Our participants well enjoy. We are expecting the such type of sessions in future also. Thank you, sir. Now I'm going to conclude the offline session of today is over. The next event we are going to start. Now I'm going to hand over the mic to Parvatavarshini to continue the next.
A warm, very good afternoon to one and all present here.